All right, Algebra 2, we are in Chapter 3, Lesson 4, about halfway through. We're still talking about inverses. So let's talk about things being functions or not functions. And the power functions are special. If I look at two power functions like f of x equals x squared and g of x equals x cubed, they are shown below along with their reflections in the line y equals x. A reflection over the line y equals x is the inverse function. Notice that the inverse of g of x equals x cubed is a function. This is x cubed, and this is the inverse. But that the inverse of f of x equals x squared is not a function. Here's the function. Here is the inverse. We have something called a horizontal line test. So if I take my pencil or a horizontal line and I cross the parabola at 2 points, it is not a function. Okay? Here, I take a horizontal line, cross it just at 1 point, no matter where I am, it is a function. So this is a no, and this is a yes. If the domain f of x equals x squared is restricted to only non-negative real numbers, then the inverse is a function. So if I say that f of x equals x squared for x is greater than or equal to 0, then I can say it is a function. It is a function, but this restriction has to be met every time. Okay, here I have the function f of x equals x squared, and look, it's restricted because we just said that the inverse of this is not a function, but I'm going to restrict it. So I can find the inverse of this. Because it's restricted, I'm not going to have any negatives. So I write y equals x squared, flip my variables, and solve for y. Y equals plus or minus the square root of x. I kept the book's graph of this function because it's much better than anything I could draw. But if we remember, our domain was restricted. X was greater than or equal to 0 is exactly how they said it. So if I graph f of x equals x squared, I'm going to plug in x values that are just greater than or equal to 0. If x is 0, 1, 2, or 3, y is 0, 1, 4, and 9. So that is my blue graph right there. Only the positive ones. And then if I do the same thing with, oops, I'm still highlighting, sorry. 0, 1, 2, and 3, I'm going to plug it into y equals plus or minus the square root of x. We actually only have the positive ones. If I plug in 0, I get 0. Plug in 1, I get 1. 2, square root of 2, square root of 3, etc. So that right there is going to be my red graph. This right here is a square root function graphed. Only the positive values. Okay? Those are functions as long as we restrict our domain. All right. Looking here, another key concept, horizontal line test is my favorite because it's my pencil. I can just take my pencil, use it with my paper, and I've completed the horizontal line test. So you can use the graph of a function f to determine whether the inverse of f is a function by applying the horizontal line test. Okay, what I have here is honestly like a pencil. Okay, you hold your pencil, you run it up and down your graph, and it just says if something is a function or not. So the inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. So if I look at this one, my horizontal line test only intersects the function once, therefore the inverse is a function. Here, it intersects the line twice, therefore the inverse is not a function. Okay, this fails the horizontal line test. This one passes. So consider the function f of x equals 2x cubed plus 1. Determine whether the inverse of f is a function, then find the inverse. I know that this is a function that looks like that. This tells me it crosses the y-axis at 1. So it looks something like this. If I perform my horizontal line test, okay, I don't have to keep on graphing it, but this is what I'm going to do. If I take my pencil and I hold it horizontally and I only cross my graph at one spot, then yes, it is a function. Cool? Consider the function, determine whether it's, and then find the inverse. So we have determined that this is a function, and since we say yes, we've determined the inverse of f is a function. Then once we say yes, I need to find the inverse. So y equals 2x cubed plus 1. Change my variables to y cubed plus 1. Subtract 1 from both sides. Divide both sides by 2. I get x minus 1 over 2 equals y cubed. Take the cubed root of both sides. I get y equals cubed root x minus 1 over 2, or f to the negative 1 of x equals that. Cool? So here we go. For some reason I erased the functions. You might want to push pause and write this down. So find the inverse of the function, then graph the function and its inverse. If I look at this one, you just have to know that whenever I have an even exponent, I'm going to have to restrict my domain, okay, because I can't have negatives. Whenever I have an odd exponent, I don't care about my domain. Anything's okay because negatives are acceptable when they're odd exponents, okay? So an even exponent, as long as my domain is restricted, will always have an inverse. So I can go ahead and find the inverse here. Y equals x to the 6th. Exchange my variables. Oops, 6th. Sorry. 6th. I should be a little neater. Take the 6th root of both sides. Y equals, I would have to say plus or minus the 6th root of x, but I don't have to say that, okay, because we've restricted the domain. So my inverse function is f to the negative 1 of x equals the 6th root of x. And both of them are graphed here, which you can just plot a few x and y points, you know, your t-table, 0, 1, 2, 3, and get your values for your y and plot it. So this could be my original, then I can do it again for my inverse, okay, and get our graphs. Okay, we have g of x equals 1/27th, x to the 3rd, x equals 1, nope, y, so sorry. I get ahead of myself sometimes. Y equals 1/27, x to the 3rd, change my variables, 1/27, y to the 3rd, multiply both sides by 27, cancels those out. I have 27x equals y cubed. Take the cubed root of both sides. I can take the cubed root of 27. I get 3 cubed root of x equals y. So my inverse function is 3 cubed root of x. Okay, and again, here my domain is not restricted, so I would set up my t-table with some variables. Plug those in. Negative 2 cubed root of negative 2. Let's see, I get negative 3 cubed root of 2. Here I'd have negative 3, 0, positive 3 root 2, and nope, positive 3. No root 2's when I'm plugging in a 1. and positive 3 root 2. So this is actually my inverse. Negative 2, negative 1, 0, 1, 2. If I plug this into my regular function, I get negative 2 to the third power is 8, negative 8. Negative 8, 27ths, let's see. Negative 8 over 27 is 0.3, negative 0.3. Negative 1 over 27 is negative 0.04. 0. I'm going to have positive 0.3 and positive 0.04. So that's how I get those very sketchy graphs. Cool? Okay, next. Third power, no restrictions needed. So I'm going to say y equals negative 64 over 125, x to the third power. Exchange my variables. Y to the third power. I'm going to multiply by the reciprocal because when things are this messy, that's the neatest way to do things. I ran out of room. Negative 125 over 64. These cancel. I'm left with negative 125 over 64. X equals y to the third power. Take the third root of both sides. I don't know why that's so long. So sorry. That gives me y on this side. And negative 5 over, I think that's 4. 4 times 4 times 4 is 64. Sweet. Cubed root of x. So that right there is my inverse function. And to graph them, there's no restrictions, so I set two t-tables. Okay, negative 2, negative 1, 0, 1, 2. I'm just plugging in my x, plug and chug, right? So if I plug in a negative 2, I'm going to have positive 5/4 square root 2. If I plug in a negative 1, I'm going to have positive 5/4, 0, positive 5, or no, negative 5/4, sorry, and negative 5/4 root 2. Okay, pretty messy if you ask me. Oh, that's wrong. I plugged that into my regular function, not my inverse function. Whew. So over here, I'm plugging this into my inverse. So I get negative 5/4 root negative 2. And those roots cancel each other out. Positive, positive, right? Put in a negative 1, negative 5/4, square root negative 1, positive, positive. 0 is going to be 0. And positive 1 is going to be the opposite of negative 1. So negative 5/4 and negative 5/4 root 2. And that's what you're going to graph. Here, I'm using this function. So negative 64 over 125 times negative 2 to the third power. Negative 2 to the third power is negative 8 times 64 over 125. I get that as a negative 4.1. Negative 64 over 125 times negative 1 cubed is going to be that negative 4.1 is wrong, I'm sorry. It's positive. Because remember, a negative times a negative is a positive. So if I input -1, I'm going to get a positive 0.51. If I input 0, I'm getting 0. If I input a positive 1, I'm going to get a negative answer. Input a positive 2, I'm going to get a negative answer. I hope you're following along because I'm making more mistakes than normal. If I input a positive 1, I'm going to get 0.5. That's what I put there, for goodness sakes. If I input a positive 2, I'm going to get a negative 0.41, a negative 0.5. Let's see if I can highlight my answers. -2, positive 0.41, -1 would be a positive 0.5, which I don't even see that I wrote. Now I'm writing it in highlighter, which is fantastic. 0, 0, 1, negative 0.51, and 2, negative 4.1. And that's what we're seeing graphing here. And honestly, I would absolutely be thrilled if you guys would open up Desmos and show me in class how you're graphing these, just to verify. It would be awesome. And we're not done. You thought we were done. We're not done. Let's do the inverse. So y equals negative x cubed plus 4. Exchange my variables. Subtract 4 from both sides. X minus 4 equals negative y cubed. Multiply everything by -1. It gives me a negative x plus 4 equals y cubed. Take the cubed root of everything. I get y to the -1 equals cubed root negative x plus 4. So there's my inverse function. I'm going to push pause and graph it on Desmos and show you guys, okay? Be right back. There we go. That's my Desmos graph, which is way cooler than any graph that I was doing by hand, right? Those were bad. Okay, next one. Let's go ahead and try to find the inverse. I have y equals 2x to the 5th plus 3. Exchange my variables. 2y to the 5th plus 3. Subtract 3 from both sides. X minus 3 equals 2y to the 5th. Divide both sides by 2. I get y to the 5th equals x minus 3 over 2. Take the 5th root of both sides, and I get my inverse. Y to the -1 equals the 5th root of x minus 3 over 2. Okay, be right back. There we go. Those Desmos graphs are so pretty. Okay, last one. Sorry about that. Y equals -7 x to the 5th plus 7. You guys are getting all kinds of practice. Exchange your variables first. X equals -7 y to the 5th plus 7. Subtract 7 from both sides. Divide both sides by -7. Y to the 5th equals x minus 7 over -7. So I just put the negative out in front. Okay, 5th root of both sides. I get y to the -1 equals the 5th root of x minus 7 over -7. Cool? And there we have exactly what Desmos would do. But I'll show you a picture. Okay, write that down because I'm probably going to put my Desmos picture over that final answer. There we go, my Desmos picture. Cool. All right, ticket prices. The average price P in dollars for National Football League ticket can be modeled by P equals 35T to the 0.192, where T is the number of the year since 1995. Find the inverse model that gives time as a function of the average ticket price. So if I have P equals 35 t to the 0.192. I can divide both sides by 35. I get t to the 0.192 equals p over 35. Now if I take this and I raise it to the 1 over 0.192, and I do the same thing here, 1 over 0.192. Right here, if I multiply both of those, I get 1. Okay, I multiply the fraction by its inverse, I get 1. So t equals p over 35 raised to the 1 over 0.92. I don't like 1 over the 0.192. So I'm going to take 1 divided by 0.192, and I get 5.2. And there is my model. Now I can use this model to predict the year when the average ticket price will reach $58. So time equals 58 over 35 raised to the 5.2. 58 divided by 35 equals caret 5.2. And I get about 14 years. So that's the years since 1995. So that gives me about 2009. Right? Yep. Now you guys will see number 11 here. I accidentally erased number 11, but you got it there, so I'm going to work with it. I've got P equals 10.7. We're talking about baseball tickets now. So I want to solve this for T. So P over 10.7 equals T to the 0.272. If I raise this to the 1 over 0.272, 1 over 0.272, these cancel out. I'm left with T equals P over 10.7. 1 divided by 0.272 is 3.7. So when are ticket prices going to reach an average of $25? 25 over 10.7 raised to the 3.7. 25 divided by 10.7 equals caret 3.7. I get about 23 years. So that would be past 1995 would be about year 2018. Cool. All right, your daily homework quiz, you have these there. These are extra problems for you to practice. You're good to go. Go ahead and practice these. I'll page through them. Please, if you have any questions on these, I'd love it if you'd ask me. Another one, I'm restricted. It's an even power, so I'm good. Okay, odd power, no big deal. Ooh, this is a good science question. Because you should have this formula memorized, especially if you're in chemistry or have taken chemistry. But that's all I got. All right, good work today. I'm proud of you all. I will see you when you're done.